We've seen that the rate at which the atmospheric pressure changes depends on the density. But that's a problem because the density of the air changes as you go up. It gets thinner. So that means the rate at which the pressure drops depends on what the pressure is. So unless we know something about how pressure and density are related, we can't solve this problem. Now we are going to make two approximations here to allow us to relate the density and the pressure. The first is the ideal gas approximation. An ideal gas is one in which you can treat all the molecules as quite independent billiard balls just bouncing elastically off each other. And it turns out that for air in the atmosphere, that's not a bad approximation. It might be a few percent out. It's a very bad approximation when gas becomes very dense, like for example in an internal combustion engine during the power cycle. But for the relatively low densities of air in our atmosphere, it's not too bad. Now, in an ideal gas situation, the pressure is proportional to the density times the temperature. So if you want a high pressure, you either have to have more gas or have the individual molecules going faster by increasing the temperature. Okay, so that's our first bit. Now we're going to make our second approximation, which is a bit worse. We're going to assume that the temperature remains constant as we go up in the atmosphere. Now that's clearly not true. As you go up from the surface, temperature goes down. It's colder on top of mountains, at least until you get to the top of the troposphere, about 12 kilometers up. After that, when you're in the stratosphere, the temperature starts actually going up as you go even higher. And then there are more spheres, the mesosphere and so on, where the temperature goes down. Basically, the physics of the temperature and how it varies in the atmosphere is a bit complicated. We could put it into the calculation, we'll see how later, but for the moment we'll just simplify it by assuming the temperature is constant, and we'll assume it's the same as it is at the Earth's surface, so somewhere about 20 degrees centigrade. How bad an approximation is that? Well, I know that when I'm sitting on a Boeing 747 cruising at 10 kilometers up, they often have those little seat back signs which tell you the conditions outside. It's often about minus 40 degrees. So the temperature at the top of the troposphere is about, well, minus 40 compared to a surface temperature of plus 20, so it's about 60 degrees Kelvin less than at the Earth's surface. Earth's surface temperature in Kelvin is about 300, so 60 over 300 is about 20%. So our pressure gradient is going to be about 20% wrong when we're at the top of the troposphere of the atmosphere, which is not too bad. Because for most of the troposphere it's going to be less than that, so it might give us maybe, I don't know, a 10% error in our densities up at 10 kilometers high, which is probably manageable. If you wanted the more accurate answer, we'd have to put in some of the physics about how the temperature changes. Okay, so if we're assuming temperature is constant, a so-called isothermal atmosphere, we then have that pressure is proportional to the density. And whenever you have something proportional to something else, you can change it into an equal sign by saying pressure equals some unknown constant, I'm going to call it C, times the density. What is C? Well, you can work it out from the ideal gas equations, but also whenever you have something like this and you want to work out what the constant is, the easiest way is just to take a known example. Our known example is at the Earth's surface. And we know that the Earth's surface, the pressure is about 101,000 pascals, and the density of air at the Earth's surface is about 1.2 kilograms per cubic meter. So if we plug those numbers in here, we end up with 101,000 equals C times 1.2. So C equals 101,000 over 1.2, which is roughly 84,000. And the units of that, I guess, are going to be pascals, meters cubed per kilogram. Not that it matters too much at this point. So we now know an equation relating pressure to density.